All right, today we're going to pop the hood on artificial intelligence. We're going to look past all the flashy demos and get right into the grease, the gears, and the real grit, the unseen engine that makes these incredible systems actually work.
So let's just kick things off with a big question. What's the real difference between an AI model that, just works and one that truly performs, adapts, and actually wins out in the real world?
Well, the answer isn't some kind of magic. It's all engineering. Or, to be more precise, it's really the art of a master mechanic. You see, building a high-performance AI is a lot like tuning a custom race car. It takes diagnostics, super precise adjustments, and a really deep feel for how every single part works together.
Okay, let's dive right in. The very first job of any good mechanic is diagnostics, right? So what happens when a model that was running perfectly in the lab suddenly starts to fail out on the track?
The most common reason, by far, is something we call drift. This is what happens when a model's performance gets worse over time, simply because the world it's living in has changed. The engine, which was purring along just fine, suddenly starts to sputter and misfire.
And here's where it gets really interesting. We can actually break down that sputtering engine into 3 specific symptoms, and each one has its own diagnostic tool. First up, you've got data drift. This is when the inputs to your model change. So imagine you trained an image model on beautiful sunny photos, but now it's only ever seeing grainy, low-light images. A simple statistical check, like a KS test, can catch that right away. Then there's concept drift, and this one's a bit sneakier. This is when the rules of the world itself have changed. Think about a model trained on pre-2020 shopping habits. It became almost useless overnight. The way you spot this is by watching to see if your model's confidence in its own predictions starts to drop. And finally, you have feature drift. This is when the most important factor for making a decision changes. You can catch this using some pretty cool tools that monitor what your model is paying attention to, like shop values. What used to be the key predictor is now totally irrelevant, and that is a massive red flag.
So this all leads to a crucial question. It's not enough to just feel like something's off. How do you actually, mathematically, measure the distance between the old world data your model trained on and the new world data it's seeing right now? And this brings us to one of my favorite analogies in all of AI, the Vogelstein distance, which is also known as the Earth mover's distance. Just think about it. It's the minimum amount of work or energy you'd need to transform one pile of dirt into the shape of another. It's such a brilliant way to think about it. This gives you a real, meaningful measure of how different your data has become, even if the 2 datasets don't overlap at all. It is the perfect diagnostic tool for our mechanic.
All right, we've diagnosed the problem. Now for the really fun part. The art of fine-tuning the engine. This is all about getting that smooth start off the line and having powerful, reliable acceleration when you really hit the gas.
And it all starts with the very first spark, how you initialize the weights. If you get this wrong, your signal can either vanish into nothing or just explode completely out of control. Think of it like picking the right spark plug for the engine. For older engine types, like those using sigmoid or tang activations, you'd use something called Xavier initialization. It keeps the signal nice and stable. But for the modern workhorse, the ReLU activation, you need He initialization. See, ReLU just chops off all the negative values, so He initialization compensates for that, keeping the signal strong so it doesn't just die out.
Next up is the optimizer. This is how the engine actually learns. A classic upgrade here is adding momentum. And this analogy is just perfect. Imagine a ball rolling down a hill. Without momentum, that ball might zigzag all over the place. But with momentum, it smooths out those little bumps and keeps a much more direct path to the bottom, avoiding all those little divots it could get stuck in.
But we can get even more sophisticated. The Atom Optimizer, it's like giving your engine an adaptive GPS. Instead of having just one learning rate for the whole system, Atom gives every single parameter its own custom adaptive learning rate. It's literally figuring out the most efficient path down that hill for every single component, which is why it learns so unbelievably fast.
Now here's a subtle but absolutely massive problem in deep neural networks: internal covariant shift. Let's go back to our engine. Imagine that every single time one piston fires, it completely changes the pressure and the temperature for the next piston in line. This forces every part of the engine to constantly have to readapt to this changing internal environment. It's just chaotic and super inefficient.
So, what's the fix? Well, it's a brilliant piece of engineering called batch normalization. And what it does is actually pretty simple. It recalibrates the inputs to every single layer, making sure they always have a consistent, stable distribution. This creates a much smoother and more stable ride inside the engine. And the result? Well, it means you can press the accelerator way harder, using much higher learning rates to train your model faster and more reliably than ever before.
And one last thing in our tuning toolkit, we have to make sure our engine parts don't become too codependent on each other. And we do this with a technique called dropout. Think of it like you're training a sports team. During practice, you randomly tell some of your star players to just sit out for a bit. The rest of the team, they're forced to learn how to play and win without them. This builds a way more resilient and adaptable final team. And in our model, it does the same thing, preventing neurons from relying too much on each other, which helps it generalize much better to new data.
So we've tuned the engine, it's running perfectly. Now, where do we actually build it? Let's talk about the high-level frameworks, which is kind of like choosing your workshop and your whole engineering philosophy.
You've basically got two main philosophies here. On one side, you have dynamic graphs, which you'll see in PyTorch. This is the build-as-you-go workshop. You can improvise, you can change things on the fly. It's super flexible, easy to debug, and awesome for research. On the other side, you have static graphs, the classic approach from TensorFlow and now JAX. This is the blueprint-first workshop. You design the entire plan up front, then you run the assembly line. What's the big advantage? A compiler can look at the whole blueprint and make massive optimizations for maximum speed in production.
But what happens when the scale of your project is just too big for one machine? Well, the first problem you're likely to hit is just having way too much data, and that's where data parallelism comes in. The solution is actually pretty straightforward. You just build identical assembly lines, you put a copy of your model on each GPU, and then you give each one a different chunk of the data to process.
But the second, and honestly the increasingly common problem, is that the engine itself is just too gigantic to fit in a single workshop bay. This is the world of today's large language models, and for this, you need model parallelism. Here, you actually have to chop the model up into pieces and spread different layers across multiple GPUs just to make the whole thing fit.
So let's bring this all together. What is the core philosophy here? What's the mindset of a master AI mechanic? I think it's this. Great AI is never a one-and-done kind of thing. It isn't just built. It's constantly diagnosed for drift, it's fine-tuned with the right optimizers, and it's meticulously maintained throughout its entire life. It is a continuous, living process of engineering. And that leaves us with a final thought to chew on. As these AI systems get exponentially more complex, is the future about training up a huge army of these master mechanics to keep everything running? Or will we eventually need to invent entirely new kinds of engines that can actually tune and maintain themselves? Something to think about. Thanks so much for joining us.